All right, along the same line of thinking, let's go ahead and revisit the electron real quick. The statement is, an atomic electron, charge Q, circles about the nucleus, charge big Q, in an orbit of radius r. The centripetal acceleration is provided, of course, by the Coulomb attraction of opposite charges. Now a small magnetic field, dB, is slowly turned on, perpendicular to the plane of the orbit. Show that the increase in kinetic energy, dT, imparted on the induced field is just right to sustain circular motion at the same radius r. Alright, so the solution for this is that initially the centripetal acceleration bounces the Coulombic force. So since we know that the force of centripetal acceleration is mv squared over r for AC, and then that's equal to the Coulombic force, go ahead and multiply the r over and solve for mv squared, and we see that the r's cancel and we're left with 1 over 4 pi epsilon naught, little q over big Q, little q times big Q over r, which again, if you remember back from physics 2, this is the energy and the configuration as well, so it all works out, looks together. The reason why we solve for mv squared is because now multiplying by half we get the kinetic energy formulation. So T is equal to 1/2 mv squared, which is equal to 1/2 1 over 4 pi epsilon naught, little q big Q over r. And then, but now after this, the magnetic field is on, and the electron circles in a new orbit of radius r1 with velocity v1. So let's do this again. The sum of forces gives us mv, that should be mv squared over r1, that should be mv1, mv1 squared over r1 is equal to the Coulombic force plus the magnetic force, which is v, or qv1b. Solve this for t1, just like we did above, and we see that we get 1/2 1 over 4 pi epsilon naught, little q big Q over r1 plus 1/2 q v1 r1b. All right, here b is equal to dB, and v1 is equal to v plus dV, and r1 is equal to r plus dr. Okay, since we're looking at little increments. So the 1 over r1 relationship in the Coulomb force equivalence, if we write that as r1 to the -1 power and then substitute in that is r plus dr to the -1, we can go ahead and factor out a -1, r to the -1 plus 1, and then inside is 1 plus dr over r. Pretty common thing there. But what we can do is approximate that the -1 relationship is approximately r to the -1 times 1 minus dr over r. So that the reciprocal power goes away in this approximation. So that's pretty clever. Now we can consider this to the first order then, and what we say is that here T1 is equal to 1/2 1 over 4 pi epsilon naught Q, little q big Q over r times 1 minus dr over r. So we're able to write r1 in terms of r only. Okay. Similarly, what we're able to do here with v is this v1 and r1 is just substitute them in. The reason why this works out is because whenever you factor it and show it to be case, it all factors the same. That was really shady. I don't know if I like the hand waviness of that. But again, since we're looking to the first order, we're not curious about what happens to dV and dr as a product later. So we're just trying to find what v and r is times dB. Okay, so this is our T1 equation now. And what we know about dt is that that's T1 minus T, the initial. And we can go ahead and take the difference, and what we're left with is QVR over 2 dB minus 1/2, and then this, after we factor, we see that we get a cancellation of terms here on the Coulomb force term, and all we are left with is that dr over r term left in everything, all things considered. So that's what we're left with is dr over r times the Coulomb energy term. Now the induced electric field is equal to E is equal to r over 2 dB dt. Again, we saw this from several scenarios. But so if we do that and we plug this in, what we see is that we have m to the force, we have ma is equal to qe, but we write a in terms of dv dt. And if we shove all this together, we get that the force is equal to qr over 2 dB dt. Solving this for mdv, we get qr over 2 dB. The increase in kinetic energy is therefore, so anywhere we see an mdv, we can go ahead and plug that in. And if we, what this means is that for dt, the derivative of this is equal to 1/2 mv squared. Or excuse me, we take the derivative of it, you get the v squared comes down. So you get mv dv, okay, makes sense. The 2 and 1/2 cancel. But now, as you saw with mdv, we can plug in a v to both sides, and this is equal to qvr 2 dB, okay, from the induced field. And comparing the two expressions, the derivative of the energy and the literal definition of step energy, dt is equal to t1 minus t, and the actual derivative from the induced field. If we set the two things equal to one another, we show that dr has to equal 0. Okay, because that whole Coulombic term has to cancel in order for qvr2 dB to equal to qvr2 dB. So, again, kind of hand wavy, but this kind of thought process is used a lot. But pretty cool result nonetheless.